Starting this two-dimensional finite element. So far we have discussed one dimensional. So main basically why we go for two dimensional finite element, because in the 1D no we assume that whatever unknown variables are there, they are only unknown function of only one coordinate, that is a coordinate along length, which we took as x. Now in two dimensional problems, because usually the two dimensions of the domain are significant and the unknown variables are functions of two independent coordinates, and therefore we need to model these problems using two dimensional finite elements. So here dependent variables, so maybe say temperature, displacements, will be function of two coordinates. So dependent variables are unknown functions of two coordinates. Of course, these are orthogonal coordinates. So say for example x and y, and so that is one that no. So that say we want to study the temperature distribution, heat conduction, steady state heat conduction in a two-dimensional domain. So then the temperature would be function of x and y. Or if we want to study a plane stress, plane strain problem, so then the displacement along x and y would be unknown functions of x and y coordinates. So then we need to use two-dimensional finite elements. And that is then in the 1D, I know you have seen that in the truss and beam we are discretizing actually one-dimensional domain, that is domain along length of the member, structural member. Here we discretize it two-dimensional domain. So discretization of two-dimensional domain. In the 2D finite element, we discretize the two-dimensional domain, and domain can be arbitrary. Either it could be a regular geometry, say a rectangle, or it can be any arbitrary geometry. So the domain can be arbitrary. Arbitrary is like, let us say you have this kind of a domain, and then you are discretizing this. So this is a two-dimensional domain, because there is no one single dimension which is significant. There are two dimensions which are important here. So this is a two-dimensional domain, and the discretization could be using triangles, quadrilaterals. So then you would discretize this into a number of elements like this. So the discretization would be, you could discretize into a number of elements like this. So this is just to demonstrate that what we would be doing in 2D problems. And another important feature is that in 2D problems, the formulation, no, of course, 1D problem we have discussed the formulation only in terms of physical coordinate, x coordinate, which is local coordinate along length of the element. It can also be done using natural coordinate, but then there is no added advantage over there. So I did not discuss that. But in 2D, I will be demonstrating that what happens if we do the physical coordinate and the natural coordinate, and what are the advantages. So formulation in 2D can be two ways. One is using the, that is basically this is based on the interpolation of the unknown variables. So the interpolation can be in terms of the physical coordinates, say x and y coordinates, physical coordinate space. and second is the natural no, the formulation can be in natural coordinate space. That is, unknown variables are interpolated in terms of natural coordinates. When I will discuss, I will tell you what do we mean by natural coordinate and how it is done, the formulation. So natural coordinate space. So first I am going to discuss the formulation in the physical coordinate space. So I will first discuss what are the different types of elements. So now in this, when you look at the elements, so now earlier no, the element was a line. In the 1D problems, the element is actually a line, what you are discretizing. So if you are using as FE package, then you don't have to create a solid. You would be actually creating just line along the center line of the structural component, and you would be discretizing that. That is what we have done in 1D problems. But in 2D, you are going to discretize actually these areas or surfaces. So the simplest element we can use is a triangle. So if you look at the simplest element in this, that is a three-noded triangular element. Three, that means one element when we are talking about. Of course, the whole structure you would be discretizing into a number of elements. So that means no, the element, if you look at the shape of the element, it is going to be a triangle. I'm sketching here only one element. So this is just the one element, and these are the nodes, corner nodes. So let us say the corner nodes are local node numbers are 1, 2, and 3, and the physical coordinate is say x and y. And at each node there is a degree of freedom. Let's say if we are talking of heat conduction problem, then the degree of freedom at each node would be temperature. If we are talking about the plane stress, plane strain, solid mechanics problem, then the degrees of freedom would be displacements along x and y. So u1, v1, u2, v2, u3, v3, like that. So depending on the problem. So if we are talking of temperature, then the heat conduction problem, then the degrees of freedom is going to be T1, T2, and T3. So at each node we have only one degree of freedom. So here, if you look at the temperature, here temperature is the unknown variable. So for heat conduction, of course, for the, as I said, for the plane stress, plane strain problems, it would be temperature T as a dependent unknown variable. So if we take temperature as a dependent unknown variable, then the approximate solution T is a now function of two coordinates, x and y, unknown function of x and y. Of course, in the beam theory also we have seen that the displacement along length is a function of x and y, but along y direction its variation is known. We assume that normal, no straight normal remains normal, or it remains straight, maybe normal in Bernoulli beam theory, and it doesn't remain normal in Timoshenko beam theory. But here, no, the t is an unknown function of x and y both. It is an unknown function. So t would be, now we have 3 degrees of freedom for the element as a whole, T1, T2, T3. So we will assume an approximate solution which has got three constants. So that is A0 plus A1x plus A2 into y. And of course, then subsequently, no, you will say that t equal to t1 at x is equal to x1 and y equal to y1, and t equal to t2 at x is equal to x2, y equal to y2, and t equal to t3 at x is equal to x3 and y equal to y3, where x1, y1, x2, y2, x3, y3 are coordinates of these nodes 1, 2, and 3. So you would express A0, A1, A2 in terms of T1, T2, T1, T2, and T3, and then you get the shape functions. Now, one thing you will notice here in the 1D problem, because no, the unknown variable was function of only one coordinate. So one of the criteria to know, assume an approximate solution is to satisfy the geometric invariance. So that doesn't there it is, no, in 1D problems it is trivial, but in 2D and 3D problems no, that becomes important. the geometric invariance. So the geometric invariance meaning is now we have assumed this as an approximate solution. And if we interchange x and y, the form of the solutions would not change. So if we interchange means it is still the same form. There is a constant term linear in x, term linear in y. So the form remains same. So this satisfies the criteria of geometric invariance. So that is to say that basically we have discussed these criteria when I had discussed the criteria for assuming the approximate solution within an element. So now the approximate solution. So other things remain same. This is the geometric invariance is the criteria which becomes important for 2D and 3D problems. So that is why I am writing it again. So approximate solutions should satisfy geometric invariance. And what that means is that form of the approximation solution should not change if x and y are interchanged. That I was just telling you for this case. So what it tells you that form of the approximate solution should not change if x and y are interchanged. So that's the simplest is a three-noded triangular element. Now we want to improve the convergence rate of the element. Convergence rate means when we increase the number of elements, ultimately the result should converge. That means if two consecutive fine meshes should give you the same result. So if we want to get result with lesser accurate result with lesser number of elements, then we'll have to go for a higher degree polynomial, and for that we have to increase the number of degrees of freedom per element. So the next possibility is that we use six noded triangular element. So six noded triangle or triangular element. So it will be, the edges are still straight here in the physical coordinate space. So it has corner nodes and then it has mid side nodes. So usually the node numbers are first corner nodes. So these are local node numbers 1, 2, 3, then 4, 5, 6. And this is one single element. When we are solving problem, obviously we would discretize a given problem into a number of elements. So now at each node you will have temperature as a degree of freedom. So here you will have T1, T2, T3, and then T4, T5, and T6. So now there are six degrees of freedom per element. So when you assume an approximate solution, you should have now six terms. Now, how do we choose those terms? So there is what is known as Pascal's triangle. So in Pascal's triangle, you have first top constant term 1, then linear terms in x and y, no linear in x terms, linear in x and linear in y. So we have x and y, then quadratic terms x square, xy and y square. Then we have cubic terms x cube. Then know the power of when we go from left to right, the power of x decreases, power of y increases. So x square y, then xy square, and then y cube, and then you have x power 4 like that. Now you can construct the Pascal's triangle x power 4 x cube y, then x square y square x y cube and y power 4, and like that. So in the three noded triangular element, if you see, we have basically taken these three terms from the top, these three terms. Now when we are going for the six noded triangular element, so we will also include these quadratic terms. So we will add basically these terms also in the approximate solution. So when you assume an approximate solution now for this six noded triangular element, we are taking temperature as an unknown. The same thing can be said for the displacements along x and y. the form is going to be exactly same. So you would see that t, which is a function of x and y, is equal to now constant term a0 plus a1x and a2y linear terms, and then the quadratic term. So that is a3x square plus a4xy plus a5y square. So these are the six terms. Now again a0, a1, a2, a3, a4, a5 would be expressed in terms of t1, t2, t3, t4, t5 and t6, and then you get the shape function. So there would be six shape functions. So we could have either a three-noded triangular element or we can have a six-noded triangular element.
Please,
Yeah, yes, please.
sir, could you repeat this? How many terms are to be taken? How do we get that? How many terms from Pascal string are to be taken? How we decide that, sir?
Yeah, so how we are deciding that, I said this element has got six nodes, and if we have around 1 degree of freedom at each node, so then this no element has got six nodes, so there would be total six elemental degrees of freedom. No, T1, T2, T3, T4, T5, and T6. So these are the 6 degrees of freedom. So we should have six terms in the approximate solution. Now, when you see the sixth term, it should be a complete polynomial. So we start with a constant term, then we should have linear term. So this makes no a0 plus a1x plus a2y. So these are the no constant and linear terms. So these are only three. Then next we go for the quadratic terms, and in quadratic we have x square, xy, and y square. So no, these three terms makes it no the six term approximation. So the number of unknown constants a0, a1, a2, a3, a4, a5 are equal to number of degrees of freedom per element. That is T1, T2, T3, T4, T5, and T6. So we will be able to express all the six unknown constants in terms of the values of T at each node, T1, T2, T3, and so on. So the six terms are based on the 6 degrees of freedom for the element. First we take constant term, then next we go for the linear term, next quadratic term, then we go for cubic, and then for quartic, and so on. So depending on how many degrees of freedom at each node we have, for the element as a whole we decide that. So here, because element has got 6 degrees of freedom, so we are taking six term solution, so
Yes,
that
sir.
we will have a unique relationship between these unknown constants a0, a1, a2, a3, a4, a5, and the values of temperature T1, T2, T3, T4, T5, T6 at all the six nodes. So these are the triangular elements. In the 2D, you could have three-noded triangular element or a six-noded triangular element. Then next we have is the next set of elements are basically quadrilateral elements. Yes, please.
So this Pascal's triangle is useful in only for
Yeah.
triangular elements, or we can use it
I
for
think your
other.
voice is not clear. Your voice is not clear. There is a lot of noise coming. I something you are referring to Pascal's triangle. So I didn't get your question, but in Pascal triangle, how we are for the three-noded triangular element, because we wanted to have only three-term solution. So we took a constant term and then term linear in x and linear in y. You could have also thought that instead of taking constant linear and in x and y for three-noded triangular element, why not to take a naught x square plus a1 xy plus a2y square? But then no, this is not a complete polynomial. So if we are having a quadratic, means before that we should have a linear term and a constant term. So it does not satisfy the completeness requirement. So that is why for the three-noded we have one x and y. For the six-noded triangular element, then we have constant linear terms and also the quadratic term from the Pascal's triangle. So next is four-noded rectangular element. Actually quadrilateral, but because
Sir,
quadrilateral is
may I know this Pascal's triangle? It is only useful in case of triangular element, or we can use it for any kind of element, maybe the
any kind
square
of
or any
element.
kind of
It,
one.
yeah, it can be used for any kind of element, not only for triangles. Next I'm going to show you that for the rectangular elements. So the next class of elements are basically quadrilateral elements, but quadrilateral elements formulated in physical quantity space do not satisfy the inter-element compatibility requirement. So I am just restricting to rectangular elements. So four noded rectangular element. So after triangle, we can have rectangular elements, and rectangular elements means then we will have the simplest is four noded rectangular element, and that's what I am talking about. And then the this is the xy coordinate. These are the nodes, corner nodes. These are local node numbers 1, 2, 3, and 4. And at each node again, let us say we have temperature T as a primary variable. So then the degrees of freedom are going to be T1, T2, T3, and T4. So these are 4 degrees of freedom now. So now we want to have primary variables as degrees of freedom at the nodes, and for heat conduction problem, temperature would be the primary variable. So therefore, at each node it has to be there as a degree of freedom. So there are now four elemental degrees of freedom: T1, T2, T3, T4. So we should choose the four terms in the approximate solution. So how do we choose that? Is again we refer to the Pascal's triangle. So we will have a constant term, we will have a linear term in x, linear term in y, and then we have to include one more term. So what should we include? X square, xy, or y square? So if we include either x square or y square, then it will not be geometrically invariant, because if we have x square and if we change x, interchange x and y, then it will become y square. So the form is different, and similarly y square. So then we take only know this xy term. So then we will take only in the Pascal triangle, we will take only these terms. So here t, which is a function of x and y, will be taken as a0, constant term, linear in x, linear in y, a2y, and then no, when we go to the quadratic, we take a term which is geometrically invariant. So we go for a3x into y. And if you have it in this form, if you interchange x and y, the form of the solution doesn't change. And we have four parameters, a0 and a2, a3. They can be expressed in terms of four elemental degrees of freedom: t1, t2, t3, and t4. So this is how we assume the the approximate solution for this case. Again, we are going through the Pascal's triangle, but we are taking the constant term, linear term, and from the quadratic we are taking only xy. So now, like four noded, you can have eight noded rectangular element. Similarly, you can have nine noded rectangular element, and most of the time we limit. So if you are using packages, so you will find that packages would have three noded triangular element, for six noded triangular element, four noded rectangular quadrilateral element, eight noded quadrilateral or rectangular element, and nine noded. So these are the most commonly used finite elements in 2D. So next is eight noded rectangular element, and the if you look at the shape of the element,
Excuse me,
we are
sir.
taking. Yeah, yes, please.
Sir, you have told about four noded rectangular elements, sir.
Yeah,
Sir, you have told them this txy is equals to a naught plus a1x plus a2y plus a2 a3xy. So
yeah.
is this the minimum requirement for the equation? If we take into account x square and y square as well, then will it improve our like result getting
Yeah,
capabilities
yeah,
or the
it will
accuracy?
be, it will improve, but we cannot have that in the four noded rectangular element, because four noded element with t as degree of freedom at each node, we can have only and only four terms. So now if we want to improve, we want to take quadratic, complete quadratic terms, then we'll have to go for more number of nodes in an element. So that's the next one I am demonstrating, is the eight noded rectangular element. So if you go for eight noded rectangular element, then you can have more term in the approximate solution. So you will find that in terms of convergence rate, say six noded, the triangular element would be will be giving more accurate results, or will give faster convergence compared to four noded rectangular element, because four noded rectangular element has got only four terms, only up to x and y, whereas six noded triangular element has got x square and y square terms also. So obviously this would be inferior in convergence rate compared to no 6 noded triangular element. But when we go for the 8 noded rectangular element, so now again the corner nodes and then the mid side nodes, that is what we have. So corner nodes, we first number corner nodes. So there are 1, 2, 3, and 4. These are local node numbers actually, and it is of course not hard and fast to number it in this fashion, but general practice is that we number first the corner nodes in anti-clockwise manner and then the mid side nodes. So 5, 6, 7, and 8. So this is x and y. And again the degrees of freedom are temperature at each node. So T1, T5, T2, and so on. So now in this case, if you look at, now there are total 8 degrees of freedom. At each node we have temperature as a degree of freedom. So therefore total would be 8 degrees of freedom. So when we assume an approximate solution, we will take 8 terms from the Pascal's triangle. So now how do we take those 8 terms? So we will take no first constant term, then linear in x, linear in y, and then we will take these quadratic terms x square, xy, and y square. So this will make basically 6 terms. So 3, that is 1 xy, x square, xy, and y square 6. And then we want to include 2 more terms. So how do we go about that? So obviously next we will go for the cubic terms. But then what we do is we take terms which are closer to the center of the this Pascal's triangle, center line of the vertical center line of the Pascal's triangle. So then we will go for x square, y, and xy square. So these will be the terms in the approximate solution for 8 noded rectangular element. So in this case, t of xy will be taken as those 8 terms I just said. So T of so in this case T of x comma y will be taken as constant term, then term linear in x, term linear in y, then quadratic terms. So we have a3 x square plus a4 xy plus a5 y square, and plus, as I said, then a6 x square y plus a7 xy square. So these 8 terms we will include, and this element will give faster convergence. That means with lesser number of elements we will get no accurate results, basically because we have more number of terms in the approximate solution. Then next label is you can go for the 9 noded rectangular element. So 9 noded rectangular element. So we are increasing only one node. So in case of 9 noded in the Pascal's triangle, we have to include one more term. So now if you see in the 8 noded, we have already included the terms which are no tick marked in green color. Now you want to add just one more term. So which one should we add? So we cannot obviously add x cube or y cube because we need only one, and if we add either x cube or y cube, the approximate solution will not be geometrically invariant. So now the we interchange x and y, the form would change. So then next we go for the quadratic term, and in the quadratic we take the one which is close to the vertical center line, that is basically x square y square. So this is the term which is the additional term would be added in the approximate solution for the 9 noded rectangular element. So that is basically now if I sketch the element. So now where will be the ninth node? That's another question. So of course we have to have the corner nodes because they define the boundary of the element, and then we have these mid side nodes, and nodes are numbered as first corner nodes 1, 2, 3, 4. These are local node numbers 5, 6, 7, and 8, and then the next 9 node is added at the center. So this will be ninth node. This is one single element. No, means now 9 nodes, and then the approximate solution for this would be t, which is a function of x and y, would be a0 plus a1x plus a2y plus a3x square plus a4xy plus a5y square plus a6 x square y plus a7 xy square and plus a8 x square y square. So these will be the 9 terms, and each node will have temperature as a degree of freedom. So all these constants a0 to a8 can be expressed in terms of t1, t2, t3, t4, t5, t6, t7, t8, and t9. No, because we would know the coordinates of the element. So the nodes, x and y coordinates of all the nodes. So we would be able to express this. So this is how, these are the, in 2D you have different triangular element, 2 node, 3 noded, 6 noded. Then you have quadrilateral elements. I am talking here about rectangular elements specifically, because in physical coordinates the only rectangular elements satisfy the inter-element compatibility. So you could have either 4 noded, 8 noded, or 9 noded. So these are the various elements are available, and obviously if you choose the element which is having higher more number of nodes, so convergence rate would be faster. So now another thing I wanted to talk about is when we assume an approximate solution. So we make sure that it is of course differentiable up to the, at least up to the highest order derivative present either in the weak form or the integral functional. That is one. So that we have not seen. When I actually develop the element level Gaussian equation, I will justify that portion. And then it should be a complete polynomial. It should be geometrically invariant. Another important thing is the inter-element compatibility. So that's what I mentioned, that the triangular elements satisfy the formulated in physical coordinate space satisfy the inter-element compatibility. Similarly, the rectangular elements formulated in physical coordinate space, that means the approximate solution is assumed in terms of physical coordinates x and y. They also satisfy the inter-element compatibility. But if I take arbitrary quadrilateral, not a rectangle but a arbitrary quadrilateral, and formulated in physical coordinate space, it will not satisfy inter-element compatibility across the common boundaries. So for that reason we go for the natural coordinate formulation. So that I will discuss when I talk about the formulation in natural coordinate space. But let me just write that no, we have to also look at this criteria. So that is inter-element compatibility. So what it basically states that primary variables should be continuous. Primary variables should be continuous across the element common edges. So what it means is, for example, no, we have a rectangular domain and discretized using triangular elements. So no, you could discretize no in this manner. So now these are the 4 nodes you have. We are discretizing this into two rectangular, no, 3 noded triangular elements. So now this is, let's say, global node number 1, 2, 3, and 4, and the elements are, this is element number 1, this is element number 2. Now this edge from node 1 to 3 is shared by both the elements 1 and element 2. So of course we will have temperature, let's say, as a degree of freedom at node 1 and 3, and we will make common T1 and T3 values for both the elements. But we have to also ensure that temperature distribution obtained along line 1, 3 from element 1 is same as that obtained from element number 2. So when we get the distribution, temperature distribution along line 1, 3 from element 1, that should be same as whatever distribution we get from element number 2. And if it is so, then we say that the element satisfies the inter-element compatibility requirement. So triangular elements satisfy that requirement, and but the rectangular elements also satisfy that requirement. But if you go for a arbitrary quadrilateral element which is formulated in terms of x and y, that is approximate solution is obtained in written in terms of x and y, then that will not satisfy the inter-element compatibility requirement. So now let's so with this little introduction to what are the different types of two-dimensional elements. Let's look at the look at the problems and formulation, more detailed formulation. And for that, I'm because 2D heat conduction problem is the simplest problem because it involves only one unknown variable. So most of these steps can be demonstrated manually. So that is why I'm choosing this. Of course, then we would be extending the same concepts to plane stress and plane strain problems. So that is means you have a seat, and the seat is subjected to say a metal seat, which is let's say part of a submarine cell, and that is subjected to in-plane forces, and we want to study the displacement, that is deformation and stresses. So we need heat, no, plane stress, plane strain elements. So I will be demonstrating that kind of element also. But 2D heat conduction problem is the simplest problem for which all the steps can be demonstrated manually, and that is why I'm choosing that. So next is this 2D steady state heat conduction problem. Yeah, so now what I'm going to do is first I will derive the governing differential equation, because now when I'm discussing in the lectures I'm covering all aspects, but when you are asked to solve a problem depending on what is asked, you have to answer only that much. No, you don't have to include all the details before solving a problem. So if I give you a problem and ask you to solve, you start with the given element level governing equations and then assembly, imposition of boundary condition and solution post processing. But if I ask you to derive the element level governing equation, then you have to start from the either the differential equation weak form or the integral functional, and then you have to show all the steps. So that is what you have to keep it in mind. So now let me say that we have a rectangular domain over which we want to study the heat transfer. Say in engine room, no, from the engine you have to dissipate the heat, and there are fins which can be treated as rectangles, and we want to model only one particular fin. Of course, in 1D we model that as a rod, but you could have actually this kind of plate kind of structure as basically the heat dissipating devices. So we are kind of modeling that. So the coordinates are, let us say, x and y, and the dimensions are along the x, the dimension is a, along y the dimension is say b, and the thickness is h. So it has some thickness. Of course, I am assuming that thickness is much smaller, so let's say h is the thickness. So first, to develop the differential equation, we will have to take a small differential element. So if I take a small element over here of lengths delta x and delta y, and if we show the energy basical exchange between the surrounding part of the this fin and the this differential element, so we will have heat entering along x direction, let us say that is qx. This is heat per unit area, so it is heat flux. Qx is heat flux along x direction, that is heat per unit area. So let us say heat entering is Qx, and then because no the other side there is a change in the dimension, so there is going to be increase. So let us say Qx plus delta Qx. Of course, delta Qx could be positive or negative. Similarly, heat entering along y is, let us say, Qy, heat flux entering along y, and heat flux leaving along y direction is Qy plus delta Qy. And in addition, let us say there is a heat generation inside this. This QG may be many problems it would be zero, but I'm taking that no, there is a heat generation. So this is QG is heat generation per unit volume, and we have already said that no, this dimension is delta x, this dimension is delta y, and thickness is of course h. So here, as I said, Qx is the heat flux along x. Heat flux means heat per unit area. Heat flux along x. Qy is heat flux along y, and Qg is heat generation per unit volume. Per unit volume. So now, know the way we did know for the 1D problem, same kind of thing we do for the here also. So we basically write the energy balance equation. So let me first write the heat going out of this. So this is heat Qx plus delta Qx, which is going out of this differential element. So Qx plus delta Qx. So this is heat per unit area. So we, for the total, we multiply the area. Area would be the area of this face. So delta y is the length and h is the thickness. So the area would be h into delta y, minus Qx is the heat which is entering. So Qx again h into delta y, and then we take off this Qy, this heat. So that is Qy plus we have delta Qy. This is heat per unit area. We need to multiply by area. We know that this length is delta x and into h. So we will have h into delta x minus we will have Qy h into delta x. And this there is a heat generation also. So this must be equal to, because whatever we are writing over here is the heat going out of the differential element. So this must be equal to heat generated inside. So Qg is the heat per unit of volume. So volume of this differential element is delta x into delta y into h. So this is what you get this equation. And now what you can do is you would see that no, this term and this term will get cancelled out. Similarly, this term and this term will get cancelled out. And then the whole thing you divide by the volume delta x, delta y, and h, and then take the limit when delta x is going to 0. So the first term will give you actually del qx by del x, this term, because when you are dividing by delta x delta y into h, so we will left with delta x upon delta qx upon delta x in the limit when delta x is going to 0. This would become del qx by del x. Similarly, this term, this particular term will give you del qy by del y and is equal to qz. So this is, let us say, equation number 1, where this equation is in terms of heat fluxes qx and qy. Now we want to express ultimately this equation in terms of only one unknown variable, that is temperature. So then the constitutive relation comes into picture. In this case, because it's a heat conduction problem, so it is heat conduction law. So we that is also we call it as a constitutive relation. So constitutive relation is, in this case for heat conduction problem, is a Fourier law of heat conduction. Fourier law of heat conduction. So in this I am going to assume that the material is linear. That means heat fluxes are linearly dependent on the temperature gradient, and the thermal conductivity is same in all directions. So I am also assuming that it is isotropic. So the material is linear isotropic material. So thermal conductivity is same in all the directions. That is what we are assuming. So as per then this, we write Qx is equal to, and because it is isotropic, there is no coupling between the heat flux along x and the temperature gradient along y. So it is only dependent on the temperature heat flux along x direction. So this is minus k into del t by del x, and similarly Qy heat flux along y direction would be minus k into del t by del y. So now we substitute these two Qx and Qy expression in equation 1. So you will find that then equation 1 can be written as basically first term. I know we have a minus sign here. We have a minus sign here. So I can write that as first term as it is del by del x of Qx, and Qx is minus k into del t by del x. That minus I have written over here. So here you have k into del t by del x. And why I'm writing this k inside, because k could be function of x and y, so it has to be inside the del by del x, the outer del by del x. Similarly, minus second would be del by del y. k into del t by del y is equal to qg. So yeah, let us say this is equation number 2. So this is now the governing differential equation of this problem. So when you look at the governing differential equation, so this is the governing differential equation for this problem, and we are interested in solving this. So when you are want to solve this equation, so as we said, we have discussed similar to 1D problems. To first we write the weighted residual statement, and then we carry out the integration by parts and write the big form. And from the big form, we can also get the, in this case, it is possible to get the integral functional. So those are the steps similar to 1D problems. Of course, now the integrations here will be to the double integrals because it involves the x and y two coordinates. So now if I want to write weighted residual statement, so as you know, now the integration, if I am writing the weighted residual statement over one particular element, so then it would be integration over area of the element, double integral, integration over the area of the element, weight function. Now the weight function is also going to be function of x and y. Earlier it was only function of x. And then the residual, and domain residual, take all the terms on the left hand side. So we will have this term and minus qg. So the residual is going to be minus del by del x of k into del t by del x minus del by del y of k into del t by del y minus qg. And then you have this integration over volume, so h into dx into dy, and this is equal to 0. No, that is what would be the weighted residual statement. And of course, if you wanted to solve the approximate analytical solution from here itself, then you will assume an approximate solution as a function of x and y, and you will eliminate some of the constants by satisfying the given boundary conditions. And then you substitute it here and take the weight functions depending on whether you then use let's say Galerkin method. So you take the weight function as coefficients of unknown constants in the approximate solution after satisfying all the boundary conditions, and then you can solve similar to what the way we did no 1D problems. But we are continuing here for further. So integration by parts. Now we want to go for the big form. So we carry out the integration by parts. Now the integration by parts. Now if you look at basically this term, so this involves no partial derivative with respect to x. So the when we take now, this is consisting of actually three terms, no, minus w into del by del x of k into del t by del x, minus w into del by del y into k into del t by del y, and minus w into qg. So now the first term involves the derivative with respect to x. So we will carry out the integration by parts with respect to actually x. So we will transfer the derivative from t to w, and second term derivatives with respect to y. So we will carry out integration by parts with respect to y, and then we will transfer the derivative from this term to w here. And of course, this does not involve any derivative of unknown variable t. So there is no integration by parts for that. So if you carry out that, so in the integration by parts, this already a minus sign over here. So the integral term will become basically the double integral positive. And if you see the integration by parts here, rather than giving the values at two boundary locations, what we had in 1D problems, it would become a boundary integral, because for this term we will carry out the integration with respect to x. So integration with respect to y will still remain. Similarly, when we are doing the integration by parts for this term, we will carry out integration by parts with respect to y. Integration with respect to x will remain, so it would become a boundary integral. So when we do this integration by parts, so what we would get is the no derivative of w with respect to x into k into del t by del x. That is the first term we will get. The second term will get del w by del y into k into del t by del y, and then of course the integration h dx dy will be there. And then as I said, the boundary integral is going to be over the entire boundary. So that I'm using, this circle means it is integration over the closed boundary, and this gamma, capital gamma, denoting that it is a boundary integral. And minus is because when you are writing the first term, so you will integrate this, so w into, basically will have minus w into k into del t by del x, and that would be at boundaries where x is equal to certain values, x naught and x1, or x1 and x2. So basically we will have the boundary term, w term will be there, and depending on the boundary, we will have nx into k into del t by del x, plus ny into k into del t by del y into h into ds. Now this will become boundary integral. I will write what are these nx, ny, and what is h, gamma, and all that. And this term of course remains as it is. So we will have minus integration over area of the element. We will have w into qg, h into dx dy, h into dx dy. This is equal to 0. So this is what is your weak form after the integration by parts. This is weak form. So here, now if you look at basically nx is the nx and ny. Let me write both together. So nx and ny are components of, if you take the boundary, so there would be, you can consider an outward normal to the boundary. That outward normal, along outward normal, if you take a unit vector, that unit vector will have components, the direction cosines, that is along x and y. So nx and ny are those. So component of unit
Excuse me, sir.
vector, yeah,
Sir, could you please explain this integration by parts once again, sir?
okay. So let me write these. Well, I'll come back to that. So along the, so nx, ny are components of a unit vector along the outward normal to the boundary. So they could change along the boundary. So these are the unit vectors, and basically capital gamma is denoting the boundary, and we have another variable s I have used. So this is path coordinate along the boundary, means basically no, it's a kind of measuring the length along the boundary. So path coordinate along boundary, yeah. And we can write basically, so let me explain that. So I just said, no, the first term, the integration by parts you are doing. So let me write the just the first term alone. So it would be something like, the first term is minus double integral, and then you have w and del by del x of, I'll demonstrate only one, k into del t by del x dx dy. So if you carry out the integration by parts, so the first function into integral of second, minus will be the first function is w, and because integration is with respect to x, so we'll get basically k into del t by del x after integration, and then integration with respect to y will remain, and this will be evaluated at a lower value of u and upper value of, say, lower, let me denote by xl, and the upper value of x is xu, and then dy will remain there. So this is the boundary term, and minus minus plus double integral derivative of first, so del w by del x into k into del t by del x dx dy. So this is what you will have now from this. And similarly, if you take minus integral w del by del y of k into del t by del y dx dy. So again, if you use the integration by parts formula, now the integration is with respect to y. So first function into integral of second, so we will have minus, and now the integration is with respect to y, so x integral would remain. So now we will have w into k into del t by del y, because the second function is integrated with respect to y. So y derivative, basically one y derivative goes, and this is evaluated at lower value of y and upper value of y into dx, and plus we will have integration del w by del y, derivative of first function into integral of second, so k into del t by del x into dx dy. So this is what you will have. So if you look at this term and this term, that is what I have written over here. So these two terms I have written over here, and this is of course the QG term, so that is coming straightforward. Now if you look at this, so this I have slightly rewritten, because now this is if you look at this is a boundary integral. So this is the integration with respect to y, so that is, it is along the x boundaries, x is equal to xl and x is equal to xu. So that I have written the kind of dy as nx into basically ds, and similarly I have written here dx as basically ny into ds, and then this we have therefore nx into k into del t by del x plus ny into k into del t by del y into w. So this is to ultimately say that finally the boundary can be any arbitrary boundary. So finally the two integrals from the boundary we are getting, that is basically this boundary term and this boundary term, they are combined into a single boundary term given by this. So as I said, dy is written as nx into ds, and dx is written as ny into ds, and then this term is written in this manner, the boundary term. So you should know basically the boundary term form is going to be basically this. So this is how we are getting basically this boundary term. Now if you look at the big form, so you can identify the primary and secondary variables. So now if you see the primary variable, so now if you look at this boundary term, this w is there. Even if you are looking at these boundary terms, no, you don't go to that. If you look at this boundary term or this boundary integral term, now these are boundary integral terms. So only w is coming. Primary variable is only w, and one needs to combine these two for the secondary variable. So in place of w, if we write t, that will be the primary variable. So in this case, simply t is temperature is the primary variable. And if you look at the secondary variable, so secondary variable is going to be now this heat flux. So which is I am denoting as Qn. Qn is nx into k into del t by del x. I am combining these two, and y into k into del t by del y. See, as I already told you that we are writing dx and dy in the boundary integrals as nx into des and dx as ny into dy, and therefore finally we get nx k del t by del x plus ny k into del t by del y. And actually, if the domain is rectangle, then the boundaries would be either nx would be no, plus minus 1 or 0. Similarly, ny may be plus or minus 1 or 0. So depending on this would simply become k into del t by del x or k into del t by del y. So there is only one primary variable, that is this combined together, and then nx into k into del t by del x plus ny into k into del t by del y. So this is the secondary variable. Primary variable is t. So now once we have done this, so next is we get to the integral functional. Of course, you would see that the 2D problems are a bit more involved. So now if you look at the integral functional, so for that we take w equal to delta t. So and no now if the boundary integral you have to keep as a boundary integral. Earlier, at the boundaries we were writing, you making use of some notation, and we are writing the secondary variable. But here we will keep it as a integral. So if you write w equal to delta t and put in this big form, so and then take delta common. So from this you will get w equal to delta t, and then you take delta variational operator common, you will get half k into del t by del x whole square, and from this you will get half k into del t by del y whole square. and this boundary integral delta will simply go, so we will have no t into no this qn, this is qn, and this will simply become t into qg. So the way we did for 1D problem. So then you can easily identify that integral functional would be half integration over the area of the element and k into del t by del x whole square plus uh, del t by del y whole square h dx dy, this integral, and then minus integration over area of the element, we will have t into qg into h dx dy, and minus we will have the boundary integral term, so we will have gamma in place of w, we have written delta t, delta we have taken out, so we just get t into qn and h into ds. So this becomes the integral functional. Now once we have done these, then we go for now the formulation. So the simplest element, as I said, is the triangular element. So we will go for that. So now let us develop the element level governing equations for the three noded triangular element. So once we develop the element level governing equations, then we can use that, for assembly and imposition of boundary condition and final solution. So next, now let us do the detailed formulation for three noded triangular element. So as I said already, the element is a triangle and three nodes. So we have these corner nodes. Our nodes are numbered as local nodes 1, 2, and 3, and the coordinates are, let us say, x1, y1. In these coordinates would be known x1, y1, x2, y2, and x3, y3. The degrees of freedom are t1 at node 1, t2 at node 2, and t3 at node 3. And this is the origin of x and y. And you can have any point p inside this, whose coordinates would be, let us say, x and y. So now if you see the, again let me talk of the approximate solution t. So I know if we look at the weight, the big form or the integral functional, highest order derivative of unknown variable t is only first derivative with respect to x and y. So whatever we assume, it should be differentiable at least once with respect to x and y. So that means minimum is we have to take a linear polynomial. So if we take linear means we have to take a constant term, and linear means a1x plus a2y. And then now since t is a primary variable, so we have to have that as degrees of freedom at the node, so that when we have the common node between different elements, we can have the same degree of freedom at each node, and therefore no we can say that at the nodes the continuity can be enforced. And then if the triangular element we see at any common edges, this variation will give you the continuity of the temperature, so it would satisfy the inter-element compatibility. Let me put superscript here because this is for one particular element. So yeah, that is what we do. So that means in this case the minimum polynomial a0 plus a1x plus a2y satisfies the differentiability requirement. That is, it is differentiable up to the highest order derivative present in the differential equation. It is a complete polynomial because we have constant and linear in x, linear in y terms, and it is geometrically invariant because if we interchange x and y, the form doesn't change, so it is geometrically invariant. And we have the t1, t2, t3 as the degree freedom at no corner nodes 1, 2, 3. So we will be able to enforce the continuity of t across the element edges through this, so it satisfies all the four criteria for the approximate solution, that is differentiability, completeness, and then geometric invariance and inter-element compatibility. Now the way we do for the no 1D problem, same thing we do over here. That is, we express the unknown constants a0, a1, a2 in terms of basically t1, t2, t3. So t equal to t1 e at x is equal to x1, y1. So I can write one equation, that is t1 e is equal to a0 plus a1 into x1 plus a2 into y1. x1, y1 are the x and y coordinates of node 1, local node 1. Then similarly t equal to t2e at node 2 for x is equal to x2 and y equal to y2. So we can write t2e would be equal to a0 plus a1 x2 plus a2 y2. And then t3e that is t equal to t3e at x equal to x3 and y equal to y3. So we write that in the approximate solution we get a0 plus a1 x3 plus a2 y3. So these are the three equations. No, these three equations you have here, and these three equations be write no, in the matrix vector form. So I can write t1e, t2e, and t3 all three put together. So this vector and the this side, no, we have all three are in terms of one set of unknown constants a0 and a2. So we want to take that as a vector. So then here we have one, we have x1 y1, one x2 y2, one x3 y3, into we have a0, a1, and a2. So all those three equations, no, can be written in this form. And this is what we call as the vector of elemental degrees of freedom. So let me call this as DE. So this is DE, and this matrix let me call as matrix A. I'm just using a notation for this, which is 1x1 y1, 1x2 y2, 1x3 y3, and into this constant set of constants let me call as a vector A. So this I am a0, a1, a2 vector I am calling as a vector A. So if you multiply by pre-multiply by A inverse, you will get vector A, because we want to write unknown constants in terms of T1e, T2e, and T3, that is DE. So we can write that as basically A inverse into DE. So this is what you have. Unknown constants A0, A1, and A2 are expressed in terms of D through this relationship, and then we substitute this in the approximate solution. So if you see, the approximate solution also can be written as 1xy, and then these unknown constants I'm taking on the right hand side, so a0, a1, and a2. So I can write this as 1xy, and this a, small a is equal to capital A inverse into DE. And now if you look at the sizes, so this is obviously, as you see, 1 by 3, this is 3 by 3, this is 3 by 1. So when you multiply, these two, this and this, you will get a 1 by 3 basically vector, and that is nothing but vector of the shape functions, the interpolation matrix. And now specifically for a triangular element, these shape functions turn out to be ratio of areas. So we call them area coordinates. So I'm denoting them by L1, L2, and L3, the area coordinates. And into this side we will have D, that is T1e, T2e, and T3e. I'm going to define what are L1, L2, L3. So this will be equal to, I'm as usual we write this as interpolation matrix H, and this is D. So H is given by this, and this is D, the vector of elemental degree of freedom. Here now, where L1, L2, L3 are area coordinates. Why they are area coordinates? Because when we multiply this 1xy with A inverse, this turns out as the ratio of areas, as I'm going to define just now. So now again let me sketch the triangle here, because I will be referring it again. So these are the nodes 1, 2, 3, and I set some point P whose coordinates are x and y. So actually L1 comes out with this inverse A, A1xy multiplied with capital A inverse. It comes out as L1 is equal to area of triangle P23. So when I am writing L1 is the shape function corresponding to node 1. So that becomes in front of a node 1 we have this triangle P23, this triangle. Basically we are taking this triangle, this triangle from here to here. So this L1 basically is equal to area of triangle uh, P23 divided by the total area. So that is area of triangle 1, 2, 3. So this is what comes out as the L1, and similarly L2 would be L2 is the shape function corresponding to node number 2. So for node number 2, we take that smaller triangle in front of node number 2. This is node number 2. A smaller triangle in front of that is going from P to 3, and 3 to 1, and then 1 to P. So this triangle, of course, we are going in the anti-clockwise order. So L2 then is basically area of triangle P31 divided by area of triangle 1, 2, 3. And similarly L3 will be basically L3 is corresponding to node number 3. So the triangle in front of that is P12. So this is area of triangle P12 divided by area of triangle 1, 2, 3. So these, that is why they are known as area coordinates, because they are ratios of the area. Although they come from this inverse, when we multiply this with this capital A inverse, we get these, but they come out to be as these ratios L1, L2, L3 as defined over here. Now if you recall a little bit of your coordinate geometry you would have done in 11th and 12th, so area of a triangle can be written as a determinant of 3 by 3 determinant. So I can write area of triangle 1, 2, 3. Let me denote it by AE, which is area of the triangle itself. So that can be written as half, and no the 1 x1 y1, 1 x2 y2, 1 x3 y3. Now here x1 y1, x2 y2, x3 y3 are the coordinates of vertices of the triangle. So the area can be written like this. So similarly, if you want to take the area of triangle, say first one we had this P23. So P23 will be, let me denote it by A1, and this A1 would be half. First P is coming now, so this is 1, 2, 3. So first row you see is the 1, and then the xy coordinates of node 1. Then 2 is coming, so 1, and then xy coordinates of node 2. Then 3 x and y coordinates of node 3. So this is P23. So first coordinates of P. P is any point x, so its coordinates are 1 xy, and then 2 means 1 x2 y2, and then 3 means 1 x3 y3. So similarly, now you can write the areas of the other triangles. So area of triangle we have P31. Let us denote that by A2, because this is coming in the definition of L2. So first P is there, so 1 xy, and then 3 is there, so 1 x3 y3, and then 1 means 1 x1 y1. And then similarly now you can write area of triangle P12 is equal to, let us say, A3. So half 1 x and y, because first P is there, 1 x1 y1 and 1 x2 y2. So yeah, now you can now if you look at, because area of the triangle 1, 2, 3 is the total area of the triangle, and let us say that is AE. So you can actually write L1 is equal to A1, that is A1 by AE, A1 by AE, and AE is the area of the whole triangle. It is independent of x and y coordinates, so I can simply write as A1 is not 2 AE. A1 is this expression. So here 1 upon 2 AE, denominator I am writing just as AE, into determinant 1 xy, and then 1 x2 y2, 1 x3 y3. Similarly, you can write L2 as A2 upon AE, which would be 1 upon 2 AE, and then 1 xy, and this A2 is 1 x3 y3, then 1 x1 y1. So yeah, this is little bit of actually the coordinate geometry we do in 11th and 12th. So L3 is A3 upon AE, which would be 1 upon 2 AE, and then 1 xy, 1 x1 y1, 1 x2 and y2. Now I think yeah, so let me just discuss the properties of these, and then I will stop. So properties of area coordinates, that is L1, L2, L3, which are shape function over here. Properties of L1, L2, L3. These are area coordinates. So properties are basically area coordinates. So if I, properties means we want to look at their values at nodes. So if I look at L1, L2 and L3 at nodes local nodes 1, 2, and 3. So if you look at L1 at node 1, so now I think let me draw the triangle again over here rather than going up and down. So this is a triangle. This is node 1, this is node 2, this is node 3, and this is point P, which is at location XY. So now you see L1 was defined in terms of basically the area of triangle P23. So when I say that value of L1 at node 1, that is at this node, that means point P will be coinciding with point 1, node 1. So then now the area of triangle P23 will become simply area of triangle 123. So it would be the ratio of same area. So this will be actually become unity. But when you look at node 2, now when I am looking at the value of L1 at node 2, that means point P is going to point 2. And if P coincides with point 2, then the triangle P23 would be simply a line. So the area would be 0, and therefore this would be 0. And same thing here at 3, if P goes to 3, then again the area of the triangle P23 will become 0. So the value of L1 is unity at node 1 and 0 at node 2 and 3. Similarly, if you look at L2, L2 is defined in terms of area of triangle P31 divided by total area. So if I look at the value of L2 at node 1 means P will go to 1. So then area P31 will become 0. So this would be 0 here. And when we want to look at the value of L2 at node 2, that means point P will go to node 2, then the area will become node 231, which will be the total area. So the ratio will become unity, and similarly it would be 0 here. So L3, if you look at L3 would be 0 at node 1, 0 at node 2, and unity at node 3. So yeah, these are the properties of these say functions. That is L1 is unity at node 1, 0 at node 2 and 3. L2 is unity at node 2, 0 at 1 and 3. L3 is unity at node 3 and 0 at nodes 1 and 2. So yeah, once we basically do this, then now we have to take the derivatives of all these safe functions and write the expressions for del t by del x, del t by del y, and then substitute that in the integral functional and get the element level governing equation. So that I will do in the next class. So I want to stop here. If you want to ask any other question, you can ask. So yeah, I just want, yeah. So yes, now any questions, doubts?